Okay, our next discussion is about finding term. So again, if future value is present value 1 plus I n, so what we now are interested in is in finding this term n. Again, let's remind ourselves a little bit of school mathematics, and let's ask this question. 2 into the exponent x is 4. Again, remember in the previous topic when we've looked for I wrote equation to you x into the exponent 2 equals 4. So it's not the same equation I am writing here, pay attention. And the question is, how do we find this x? Well, now you can tell me that it's 2 because 2 exponent 2 is 4. But again, I'll say that what if I change this to 5? If the result of the exponent is 5. So then you cannot right away tell me what that x should be. So we need some technique to find that x. Well, you can say, what if I use that previous technique of finding 1 over x exponent? What happens? Okay, it doesn't hurt to experiment. So we can say, okay, 2x, 1 over x equals 5, 1 over x. You can say, okay, let's try that technique. Indeed, it will be 2 equals to 5, 1 over x. And you end up with an equation which is even worse, because now your unknown is in the denominator here. So it doesn't work. That technique would not work. We need some other technique. Okay, so the other technique is in using logarithms. Well, in our course, we do not really need to speak too much about logarithms. It would put us too much far off. You really need to know only one thing about logarithms. And that thing will be what we call power law. And based on that power law, we'll be using logarithms to generate a formula that you will be using later. You will never need to use logarithms directly. You only will need to know how to calculate them in a calculator, so you don't need to get too much scared if you forgot information about logarithms. So the power law says that if I have a natural logarithm, and what natural log is really not important right now, but if I take that natural log of any exponent, so that exponent will come in front of that natural log as multiplication. You see, so when natural logarithm acts on exponent comes in front as multiplication. Okay, so in fact, power law will work not only for natural logarithm, but for any logarithm. The reason we will use natural log is because your calculator has built-in function to calculate natural log. That's why we use natural log. Okay, so what this does is that logarithm has a very nice property that it converts exponent into multiplication. That's the power of this technique. How can we use this technique to solve this equation? Well, we will be using this logarithm on both sides, because it's an equation, we have to use it on both sides. Then it will be x times ln2 equals ln5, and x will be ln5 over ln2. Now, and that's the kind of result we are ready now to calculate using our calculator. Any calculator has that natural logarithm built in, and all you need to really do is just to say 5, and finding logarithm of that will be 1.609437912, right? So And then 2 natural logarithm, it will be 0.693147181. So the result will be that x is 2.32 if rounded to 2 decimal places. Well, what just happened right now is a little bit a reminder of your high school, I think, program in terms of how you would solve these equations. If you didn't understand much so far, that's because you probably forgot about logarithms, or maybe you didn't study them in school. In any case, you need just to not be too much scared here. I showed this to remind you, but if you didn't understand much of it, that's okay so far, because we will generate a formula that you will be able to use. What will be important for you is to be able to use that formula properly. And this just shows a little bit of why that formula is what it is. That was my goal to show you. And exactly how will we get that formula using natural logarithms? Well, let's start from here. So we have future value divided by present value. It will be 1 plus I n, right? So we need this n. We will find natural logarithms on both sides and use that power rule. N will come in front as multiplication, so that's multiplication. As a result, you will have formula for n, which is logarithm future value divided by present value divided by logarithm 1 plus I. Okay. That will be the formula which we can use now for finding term. What you really need to know in this course, to be successful in this course, how to use this formula, how to calculate everything in this formula. And hopefully what I just reminded you about logarithms, hopefully that will help you to understand how this formula for a term is connected with that original future value formula. Okay? But going forward, we will focus on only this formula and how to use it. Don't be too worried about logarithms if you don't really know what they stand for and what they do. It's actually a good idea for you to review. It's a good idea to check them out separately for you to have a little bit deeper understanding of this. But for you to be successful in this course, understanding really of these functions, which are natural logarithms in this case, that's not really that much necessary. So let's proceed to using this formula in problems. So let's write it. How much time is required for $3,000 to grow to 3,500 at 2.5% compounded monthly. How much time is required for 3,000 to grow to 3,500 at 2.5% compounded monthly? Okay, so once we already know the formula, we'll be using that formula right away. You will see it's very simple job to compute it. What is a little bit harder actually in these problems is to interpret your result. That will be a little bit, it's not hard, but you do need to understand what's happening with your investment and how to interpret that result in terms of time. We'll discuss that later. Now let's use this formula. So it's going to be ratio, which is here logarithm future value divided by present value, divided by logarithm 1 plus I. It is important to use this formula properly. So we have here logarithm, and then future value is 3500, which we divide by 3000 here, 1 plus I, which is 0.025, divided by 12, because this rate is compounded monthly. So now, how do we compute it? Well, it's our first calculation apart from that simple example that we had. First calculation with logarithms. But you will need to follow BADMAS at first, which is you need to calculate everything which is in your bracket. And then actually to calculate logarithms is very simple. Once you find that number, you enter it in your BA2 professional or BA2 business analyst calculator, after which you will press the button which is LN button on that calculator. So, and the same thing here. You will find this bracket and then you will press that LN button on the calculator and it will give you the result of using that logarithm. But I'll be very detailed here so that you can also practice with it. You can compute these logarithms separately while listening to this class right now, and you can see that if you are doing it correctly or not. So 3500 first divided by 3000, right? So it's going to be 1.166666, and then I'll press logarithm on this calculator, and what it will be 0.1541568. So I keep all decimals here. Okay, so then I'll keep it in the memory of this calculator, just to have it in future for other calculation. So now I calculate this part, which appears to be 1.002083333 and so on. I press logarithm and I get this 0.002081166, right? So now I need just to compute this ratio. The answer is 64.07. 07. In fact, I will keep all decimals right now. I'll explain you why later. So 0.0693749. What I know for now is that I have 74 periods. Now, what is that period? Basically, all this number means it's 74.069 and so on month. So this is number of months. It's very important to keep in mind that when you use this formula for n, that's the total number of periods. And I got here 64 month. Now, let's try first to see, okay, so how many years is that? So all this is how many years? Well, you can say, let me erase this. So if you divide that by 12, right, you will get, because this is 74.06 and so on, month. So you divide that by 12 to get how many years? So it's going to be 6.17244.791 years, right? So it's 6 whole years, and then there will be some fractional component here, which we can interpret in various other ways which could be necessary for this problem. Well, I know for sure that it's 6 years, right? So, or okay, I can just write it 6 years and 62.94 days. So 6 years and 62.94 days. Okay, if you want now report it in month, so you take that fractional component, multiply by 12, right? So it's going to be 6 years and $2.07 months. Right? So these are the couple of examples how I can now report my solution, my answer. Now, of course, if you are asked in this problem, give answer in, let's say, days, in years and days, then you will need to round these days up to the next day, right? So you will need to report it as 6 years and 63 days. Okay, so that will be the answer in terms of years and days. Now, if you are asked to report in terms of month, you actually will need to round this month to the next whole month, which is 6 years and 3 months. So keep in mind that in these investment problems, when you find term, unless you're requested otherwise, unless you're directly requested to round down, you always round one period up. So for example, in this case it's 2.07, right? So if I just do simple rounding, it will be 2 months. But in our investment problems, we have to round up to the next requested period. So if the question was how many years and month required, then you will round to the next whole month, so which is 6 years and 3 months, not just to the nearest digit here. So it all will depend on how the question is phrased in terms of what exactly the time you need to give as your answer. Is it years or alone, or years and days, or years or month? But if the problem mentions nothing, just how much time, so that could be the answer, which is 6.17 years. By the way, years you are not going to round to the next 6.17 years. So it's not like we report 7 years, right? So when you just give your answer as a general answer in terms of how many years that is, you usually will keep that decimal in place. But when it's a little bit more precise answer you're trying to give, you will get to the next whole period. Unless the problem asks you to find that answer exactly and to keep your month or days fractional, which you also can do, right? If the problem requests. However, keep in mind that rounding days up makes complete sense because you don't get any interest in between each day. So when you round 62.94 to 63, it makes complete sense. Whereas when you round 2.07 months to 3 months, so that will entail a lot of loss of precision, because 2.07 you basically add the whole new month where a lot of interest will be accrued, right? So if you go from 2.07 to 3, you should expect that you will overshoot your future value quite a bit. So here's our next example. How much time let's now specify this time, as many problems would do, in years and months will be required for an investment of $20,000 to accrue interest amount of let's say $2,500 if the nominal interest rate is 3% compounded semi-annually. So how much time in years and months will be required for an investment of $20,000 to accrue interest amount of 2,500 if the nominal interest rate is 3% compounded semi-annually? So notice here we're not given the future value directly, but we're given interest amount. So what this means is that we can use the formula still, but we need to be careful when we put future value. So it's logarithm of future value divided by present value divided by logarithm 1 plus I. Now logarithm, on top we have $20,000 is the investment amount plus 2,500, that's your future value, right? So it's 22,500 divided by 20,000. Okay, so that's the place to be careful about, to make sure that you add interest on top of this present value. And 1 plus I, and the rate is 0.03 divided by 2. So we'll be using this now to calculate. We'll use calculator now to calculate everything necessary for this for this formula. So I get 7.91094776. Now it is important to remind ourselves what we just found, right? So we found semi-annual periods. Right? We found that we have almost 8 semi-annual periods, which means that we are at almost 4 years here. But the question is about years and months. Okay, so let's find first how many years exactly that would be. So we divide that by 2 because there are semi-annual periods here. So we have 3.955. I think that will be enough precision for me if I round to 3 decimals here. But if you don't have that much experience with problems, it's better to keep all decimals to make sure that your answer is correct. Okay, you know what? Let me just write it all here, just because maybe you want to verify everything as you listen to this class. So 3.9554738 years, right? So that's how many years. So the answer should be stated in years and month, so which is 3 years, and so we take now this here fractional part and multiply by 12. And we obtain it's going to be 11.47 month. But we will actually write it's 12 month, right? 12 month, okay? Because we rounded up. In reality, in the exact terms, it is 11.47 month. But we round up based on what we talked about. So 3 years and 12 months, which of course actually is the same as 4 years. By the way, as always we do, it is helpful to double check and verify and also see what happens in terms of our rounding, right? So how did our rounding overshoot the necessary interest amount? Because you realize that we have 4 years here, but we rounded up, which means that the investment will be growing for a little bit longer, and we will overshoot this 2,500. Okay, so let's find future value, and that will be 20,000 invested at 3% compounded semi-annually for 4 years, right? So 12 times 4 according to our solution. So let's now compute that. So the answer is I get 22,529.85. So that's shows to us that we get extra money, right? So we get extra $29.85, and again that's because we rounded up, right? So in reality we should not wait full 4 years to get exactly $2,500, but because we rounded up this answer, therefore you get that bigger interest. In many problems also you will see, because of this kind of effect that you typically would round up your answer, because of that a lot of problems will mention that it is at least some amount of interest that you need to look for. So in many cases you will see problems which will be phrased like that. How much time in years and months will be required for an investment of $20,000 to accrue interest amount of at least $2,500 if the nominal interest rate is 3% compounded semi-annually. So this phrase "at least" in those problems basically allows you to safely round up your answer without worrying that you are going to overshoot that interest amount. Okay. Now, even if this "at least" is not mentioned, typically you will still round your answer up to the next reasonable period, because even in our everyday transactions, you're not going to go to the bank in the middle of the night to pick up your interest, right? So you will still wait till the next work day to actually go and pick up your interest from the bank. So in real life also you will basically round that period up, because you will wait for the beginning of the next period to go ahead and take your investment. So it's quite reasonable to round your time up. But let's consider one more problem. So how much time would be necessary to triple an investment at 4% compounded annually. Let's do it annually right now. So how much time would be necessary to triple an investment at 4% compounded annually? Now, let's give your answer in years and days, like this. And maybe to be more precise in our question, we can also add here to at least triple an investment. So how much time would be necessary to at least triple an investment at 4% compounded annually? Again, we will use the same logic, going for each dollar of that investment. So $1 must be $3 in this case, right? Because triple means becoming 3 times bigger. Our formula is logarithm future value divided by present value divided by logarithm 1 plus I. So in this case, logarithm 3 over 1, right? So future value is 3 because $1 becomes $3, and logarithm 1 plus 0.04. So I don't have to divide this 0.04 by anything because that's compounded annually rate, and in compounded annually rate, nominal rate and periodic rate coincide the same. So we will now find number of years directly. Okay, so the answer is 28.011.02276. Now, of course, that's 28 years because the rate is compounded annually. So I already know that it's 28 years. But what about this part? How do I convert it to days? Well, I just take that fractional part, which is I take 0.011 and so on, and multiply by 365 and round up. So and 5 days, five days, because I get my answer in terms of days is 4.023 days. So I round up to 5 days. So it looks like it's going to be 28 years and 5 days to at least triple. So that means that you will wait until all 5 days pass, even though the answer shows that if you want exactly to triple, you have to go in the beginning of day 4, right? But you still will go at the beginning of day 5 because you rounded up. Okay, so that's how you would go about this, but let's check. Let's check because it gives us additional practice with solving for future values as well. So we'll take, and to noticeably see what's happening with our rounding up. You see, if I now find future value for $1 only, maybe I will not notice that, a huge discrepancy here because of rounding up. And let's just take a very big amount, like $1 million, and see if that's going to become $3 million if I wait that much time. So I'll take $1 million and invest at 4 years, and it's a compounded annual rate, and that means I'll wait for 28 years plus 5 over 365, right? So that will be my exponent, 28 plus 5 over 365. So I remind you that that's compounded annually rate, which means that here I have total number of periods. In this case, it's going to be total number of years, because each period here is 1 year. Let's see what would happen here. So it's 3 million 314.87. Okay. So that's why I took $1 million here to make that checking, right? If I took $1 only, I would probably think that there is no discrepancy at all. But because I made that, rounding up, you can see that actually you overshoot for each $1 million, you would overshoot for 314.87. And that's why this at least here, at least triple, makes sense, right? So you at least make $3 million for each million, at least, but not exactly, because you'll get a little bit more, okay? But, this checking is important for me because now I know that my answer is correct. And I'm not very nervous about this extra money that I earned because I expected that due to my rounding up, okay? Now, actually, I want to use this problem also to show you that you should be cautious about, this rate and how it is phrased here. So it's compounded annually. Let's just pretend that this problem was PA, right? And the reason I want to show you this so that you are careful about rates. So if this problem, you see, I only changed one letter basically here. It's C, I changed to P, which is compounded annually rate. I changed to simple rate because now it's PA, means per annum, and we already talked about if there is no direct word that rate is compounded, actually that rate is simple rate. So what that means, if the rate is simple rate, then it means that over the whole term you will not be able to make any reinvestment because for simple rates usually the account will be locked. If it is not locked, then people can make themselves artificially any kind of compounding they want by a reinvestment. So in this problem we assume it's a simple rate. I just want to show to you how you would change your solution if it was just simple rate, not compound rate, right? Now, because it's a simple rate, you want to triple your investment, which means that you want to go from $1 to $2, right? So your principal is 1 and your simple future value would become 3, right? So in this case, what is your interest? Your interest amount is your simple future value minus principal, which is 2. So that's going to be your interest amount, right? And you will now use this I equals PRT formula, which from which you can deduct time, right? So T will be I divided by PR. Okay, so what is I? I is 2 divided by principal, which is 1, times R, which is 0.04. So what that will be is 2 over 0.04. That's of course going to be 50 years. Right? 50 years. Okay, so that's just to show you how much, a difference it is in both ways to think about difference. So it is a difference in terms of how much time you need to wait. So if it's a compounded annually rate, you need to wait 28 years and 5 days. But if it is a simple rate, you have to wait 50 years, almost twice as long, right? So that's really drastic difference between rates. Also, another difference, which is a huge difference, is in the solution. Okay, so the solution is completely different. Once you have a simple interest, the solution would completely change, and that you need to appreciate. Okay, let's now consider an interesting problem which will combine both finding I, finding your rate, and also finding term, finding M. So this problem reads like this. You invested $10,000. After 2 years, you notice that you earned $500 of interest. If interest is compounded annually, and if it is the same for all the term, how much time is necessary for you to earn additional $500 of interest? Now, this problem will require you to find what is that rate compounded annually, which is going on here. So we'll find the rate using formula for I. Future value divided by present value, 1 over n minus 1. Okay. So future value in this case is 10,500 because you're required to make $500 of interest divided by 10,000. 10,000, it looks like 101,000, but it's 10,000 of course. 1 over 2 because there are 2 years in that period for you to get $500 of interest minus 1. Okay, so now let's calculate that. So 0.0224695,077. Well, I is the same as J in this case because this rate is compounded annually, right? So therefore, I can just use that as my nominal rate to continue solving this problem. But let me write it here. So rounded to 2 decimal places is going to be 2.47%. That's of course is a rounded value. Okay. So now I will be using that rate for the second part of the problem. And the second part of the problem is about time. How much more should I wait to get my additional $500 of interest? So that will call for formula for n. We have logarithm, future value divided by present value, then logarithm 1 plus I. Okay, so we have on top logarithm. Future value is $11,000 divided by $10,500. Then we will divide by 1 plus 0.0247. All right, so I need to explain something here. So why is it future value $11,000? Because now $10,000 accrued additional $500 of interest. Now I'm dealing with $11,000 of future value. Now, why is the present value 10,500? Because after 2 years, my investment already has become 10,500, right? So therefore, my present value already is 10,500 after 2 years. Now, let's calculate what that is equal to. So the answer is 1.906566861, okay? Which is, use another marker here, which is 1 year. Let me convert this to days. So I'll take this fractional component and I'll convert to days. For this, I'll take that decimal part and multiply by 365 and round up. So in reality it gives me 330.9, but I'll go to 331 day. Okay, 1 year and 331 day. So here is an interesting observation. In the beginning of solution, we basically said, okay, it took me 2 years to get $500 of interest. Will it take me another 2 years to get another $500 of interest? And the answer is not exactly so. It's not that it's exactly 2 years to get another $500. In fact, you're a little bit short, right? You're a little bit short. You fall behind full 2 years here. And it's not because of any kind of rounding. We did round this rate, but the reality is it's because your present value actually changed, right? So after the first 2 years, your present value became $500 more. So now you have that additional interest that helps you now to accumulate another $500 of interest quicker than it took you to accumulate first $500 of interest, right? So think about it. To get first $500 of interest, you had $10,000 in your account. But to get the second $500 of interest, you already have $10,500 in your account, right? So it takes you 1 year and 331 additional day to accumulate 500 more interest. And in the style of the previous discussion, maybe because we rounded this up, so it's at least, right? So that's a little bit more appropriate. So because rounding up here and this at least, they kind of work together to, this at least clarifies that rounding up will overshoot that interest just a bit. Okay, so that's it for this topic of finding term and finding rate. Now we'll proceed to discussing finding equivalent rates. So that's also going to be very important for us, especially because that will be used in annuity calculations a lot. Now we start discussing equivalent rates. So for example, let's take 10% compounded monthly. It is a good question to ask, what rate is equivalent to this 10% compounded monthly? More precisely, what nominal rate compounded daily is equivalent to 10% compounded monthly. What nominal rate compounded daily is equivalent to 10% compounded monthly? Okay, so there are a bunch of questions that are arising here, right? So what it means to be equivalent, that's first question. Also, over what time, right? So that's another question, like that another rate is equivalent to 10% compounded monthly over what period of time? So we'll try to figure out all those answers to those questions. Okay, so first, what does it mean for the rate to be equivalent? Well, equivalent means giving you the same benefit. And in terms of rates, the same benefit means the same interest. Or in other words, these rates are supposed to give you the same future value. Okay? So let's say you have some two investment opportunities, right? So first investment opportunity is A. Here you have 10% compounded monthly. And let's say you have some investment opportunity B, where there is some rate J compounded daily. So the question now arises, okay, how do we find this J, keeping in mind that both this place A will give you the same future value as place B. Okay. Now, if you invest $1, because $1 is the easiest amount to invest, for 1 year, because 1 year is the easiest time for calculation to invest, we can verify if the future values are going to be the same, and based on that idea, we'll build our equation from where we'll be looking for this J. So let's go ahead and do this. In place A, we'll invest $1. So let me write this. Maybe I can erase this part. And here I'll say, in A, I'll invest $1 for 1 year. Okay, so this I do here. And also for investment B, I also do the same thing. I invest $1 for 1 year. Okay. So I do the same thing. Let's just divide this board into two parts. So what happens with this $1 in place A? Well, $1 will grow at 10% compounded monthly for 1 year, right? That's what it means to find future value of $1. Actually, I should have used the red marker here. So, and I'll just do this one. It's $1, 1 plus 0.1 divided by 12. Because multiplication by 1 doesn't change anything, you can just remove this one. And here I have the same thing. Future value will be 1 plus 0.0 some I, right? So 1 plus I, because I will correspond to this j. Remember that I is j over m, right? But it will be future value 1 plus I, whatever that I is, for the same year, which in this case is going to be 365, because this rate is supposed to be compounded daily. Well, now I can remove this, and you can see that for this place of investment, which is A or red, for this to be equivalent to this place of investment, which is B and which is blue, what it must be that 1 plus 0.1 divided by 12, I'll use the black marker, which will correspond to this part, will equal to 1 plus I, 365, right? So that's what the equation must be. So this future value must be equal to that future value. And if that is the case, after 1 year, what that equation will apply is that this I will give you the same benefit as that 0.1 divided by 12 as periodic rate. Okay, so how do we find this I from here? We can use the technique we already learned, and that is dividing by this exponent 365, right? So 1 plus I from here will be 1 plus 0.1 divided by 12, 12 over 365. Why? Because we divide this rate by 365 and we do the same on this side. We divide this by 365 to get rid of this 365, right? So from here we'll find our I, which is this minus 1. And that's how we find this periodic rate, which is equivalent to another rate. So let's calculate this. Let's find the answer, and then we'll proceed to speaking about a general formula that you can use in your problem solving. So 0.1 divided by 12 plus 1 divided by. So this I is going to be 0.0002 72875. Now J is I times 365. Now once again I want to remind you that you always need to keep all decimals in place here, because next step, which is finding J, will rely a lot on your precision, right? If you round it too abruptly, so then this will be incorrect. So times 365, and you get this answer here, 0.0996, okay? So which means 9.96%. Which means that 9.96, let me write it now here. .96 compounded daily is equivalent to 10% compounded monthly. Okay? Just to reiterate, these rates are equivalent because they generate the same future value. So we took $1, we invested with 10% compounded monthly for 1 year, and we compared that with $1, the same amount, $1 invested for the same time, 1 year, at unknown rate, unknown periodic rate I. We built equation based on that, and we found from that equation that that equivalent nominal rate should be 9.96 compounded daily. And that's not wonder, right? Because look, this rate is compounded daily, which means it's a more powerful rate. It generates more interest. So therefore, to be equivalent to this 10%, right? So this nominal rate should be a little bit lower. Because it's a little bit lower, it will be, but because it is also more powerful in terms of compounding, it will catch up with this rate exactly to give you the same future value. Okay? So another question in this discussion was, well, if these rates are equivalent for 1 year, that's because that's how we found this 9.96%, right? If these rates are equivalent for 1 year, are they going to be equivalent for more time, let's say for 2 or 3 or 4 or whatever years, right? So to answer this question, let me remind you this equation that we had. So we had 0.01 divided by 12, which is future value of $1 after 1 year. That is equal to 1 plus I, the new rate that we found. In this case, it was 0.0996 divided by 365, right? So 365. But that was our original equation that we used to calculate I, which helped us to find this nominal rate. But the reason I restored that equation right now is because I want to show you why, when these rates are equivalent for 1 year, they are going to be equivalent for any number of years. Basically, I can always, multiply both sides by some time t, and you can realize that this t can be deleted from both sides, can be added or deleted without harm for the equality here. So, in other words, if I had, for example, more time, if I compare these equations not for 1 year, but let's say for 4 years, right? So if I said, let me verify equivalence over the course of 4 years, not 1 year. So you can realize that I can simply delete this, extra 4 years from both parts of this equation, and I will be back into the situation of 1 year. So what this shows is that if two compound rates are equivalent over the course of 1 year, they will be always equivalent for any amount of time. Now, what is especially important is that this will not be true for simple rate. That is not correct. Okay, so if one compound rate is equivalent to simple rate of the course of 1 year, it's not going to be the same for 2 or 3 years. For the reason for this, we'll discuss at the end of this class. Okay, but for now, let's practice with this idea, and more so, actually, let's come up with a formula for this idea. Okay, so we have now some rate. Let's call this first rate J1. So it's known. It's known rate J1. and it's known nominal rate compounded m times per year, right? So the same thing, I can say that I have some rate J2, which is unknown rate. Compounded, so here it's M1 times, because it's J1, so compounded M1 times, and say J2 compounded M2 times. So the same thing, in order for me to find this J2, first I actually will need to find I2, right? So let's find I2. Now, what is I2? Just to remind you, I2 is going to be periodic rate corresponding to J2. So somewhere here, I'll say that I2 is J2 divided by M2, right? Now, I1 will correspond to this I1. So maybe I should just also remind you this fact here. So I1 is going to be J1 divided by M1. So in order for me to build an equation, now I can erase this because you can keep this in mind. Okay. I will invest $1 at some rate which I know for M1 times per year, right? So that's the future value of $1 invested at periodic rate I1 for 1 year, and that should be equal to I2 M2, right? Perfect. So from here, I need to find I2. I'll follow the same process as I did in my example, and if I follow that process, you will see that I'll get this formula. So I basically find the exponent which will get rid of this M2, so I'll divide everything by M2 on both sides. So this exponent will go away, it will become 1 actually, and then I'll transfer this 1 to this side of the equation. So now I have my formula for I2. By the way, this formula will be extremely important for annuities. So this formula is extremely important because in another part of the course you will talk about annuities, and in those problems you will use this formula for I2 quite a lot for some type of annuities. And if you don't get it right now, by the way, chances are that you can actually answer incorrectly many problems. And if your test, let's say, has 10 annuity problems, just because you misunderstand this part, out of those 10 problems you could fail, let's say, 8 problems, right? So that's very important to really comprehend this part. Even if you didn't completely understand how we got this formula, you still need to learn how to use it properly and efficiently. Okay? So let's consider an example now, how we would use this formula. So first, just to practice a little bit more with this idea, let's have this. If, okay, like this. What rate compounded quarterly, what rate compounded quarterly is equivalent to 7% compounded daily. So what rate compounded quarterly is equivalent to 7% compounded daily. Okay, so let's remind ourselves that formula. So I2 is 1 plus I1, M1 divided by M2 minus 1. Sometimes this subscript 1 is not written, it's just one I without 1, which means just it's first I. But it doesn't matter, as long as you understand that this I1 stands for the known periodic rate, right? So we know that this known periodic rate is 0.07 divided by 365, because this first rate is compounded daily. Okay. Now your exponent is, again, m1, how frequently that first rate is compounded, which is 365 divided by 4, because m2 is how your second rate is supposed to be compounded. Just one easy way to kind of remember this and orient yourself is that if you divide this rate by 365 here, so if 365 here is the denominator, it's actually going to be the top part of the fraction, the numerator of the exponent. So let's now calculate this. So the I2 is 0.017652315. Now, that's I2, right? So what is J2? What is that nominal rate? So when I say what rate, I didn't write here what nominal rate, but when I don't write nominal rate and just rate, that implies nominal rate. By the way, not on all problems you will be asked what nominal rate, right? So if the problem says what rate without specifying is it nominal or periodic, you should understand that it's actually going to be nominal rate. So if nothing is mentioned, it's nominal rate. If periodic rate is mentioned explicitly in the problem, so you'll be looking for periodic rate. So that's the periodic rate here. So we take that I2, which is the periodic rate, and multiply by 4, because there are 4 times that it should be compounded. And the answer is 0.070609259. So 7.06%. Okay? 7.06%. So again, you can see that the rate now we're looking for is less powerful than the compounded daily rate, right? It's compounded quarterly, it's compounded less frequently than compounded daily rate. As a result, it should be just a little bit higher to compensate for the fact that it's compounded less frequently. Okay? Again, so that's how you would go about using this formula. Okay, so of special interest is looking for compounded annually rate and solving problems involving equivalency with compounded annually rate. So let's have a very important definition for us, and this is effective rate. Effective rate. So what is effective rate? Effective rate is equal to rate compounded annually, right? So in your textbook, that's what is meant by effective rate. Okay, so that's the rate which is compounded annually. As soon as you see this term effective rate in your problems, keep in mind that actually you're asked for the rate compounded annually, and there is nothing more to it really. So to find effective rate is the same as to find compounded annually rate. So let's now solve problems involving that. So first one, I can ask this question. So what effective rate is equivalent to 5% compounded monthly. So what effective rate is equivalent to 5% compounded monthly? So as soon as you see this effective rate, it's rate compounded annually. So you can read this problem as what rate compounded annually is equivalent to 5% compounded monthly. So you'll use still the same formula for I2 that we discussed, which is 1 plus I1, M1 divided by M2 minus 1. So you use the same formula, and let's plug it in. So now I1 is known periodic rate, so which is 0.05 divided by 12. Okay, M1 over M2. See, so it's going to be 12 because M1 is corresponding to this known rate, right? So M1, it's 5% compounded monthly, so it's 12 divided by 1. So M2 corresponds to that effective rate, so which means that the rate compounded annually, so it's divided by 1, minus 1. Okay. So let's calculate this. And the answer is that I2 is 0.051161898. Now you need to keep in mind, because that's effective rate that we looked for, and which is rate compounded annually, I2 is the same as J2, right? Because J2 is basically I2 times 1 in this case. This rate is compounded only one time per year. So the answer is J2 is 5.12%. So we found that effective rate. Now, in the textbook, there is a formula which specifically is targeted for effective rate, but that is just the same formula in disguise, right? So the way it will look like, if that formula is, for the effective rate, so for effective rate it will be F instead of I2, just to specify that how special that rate is. It's going to be F, which is the same as I2 in this case, or the same as J2, because it's all the same. I2 is the same as J2 for compounded annually rate, and F will now be the new letter for that. So it will be 1 plus I, so the rate you're given basically, and will be M times that I is compounded minus 1. So sometimes you can see this formula, but you need to realize that this formula is exactly the same as that formula, so you don't need to memorize new formulas actually, right? So M2 in this case is going to be 1, so therefore there is nothing here, and subscripts are removed now, just to basically keep it cleaner, this formula. But in reality, this formula for effective rate is the same as this formula that we always use for any equivalent rate. Okay, so let's look at one more problem, and in this case I'll go reverse and I'll say this: what rate compounded semi-annually is equivalent to the effective rate of 4%. So what rate compounded semi-annually is equivalent to the effective rate of 4%? Okay, so let's use the same formula that we have. It's a universal formula for any kind of equivalent rates. So 1 plus I2, 1 plus I1, and 1 divided by M2 minus 1. Okay, so now 1 plus I1. What is this I1 now? We are given now effective rate here, right? So which is 4% compounded annually. So I1 is going to be 0.04 because now I'm already aware that I1 is the same as J1. So this periodic rate is actually 4%. And how much is this compounded? One time, right? And how much is M2 supposed to be compounded? 2 times per year, because M2 is corresponding to, just maybe to make it clear, right? So it's semi-annually. I need 2 here in my M2 and minus 1. So let's see how this works. So it is 0.0198, right? So rounded, of course. So the answer is 1.98%. Compounded semi-annually, of course. So 1.98% compounded semi-annually. That's a periodic rate, by the way. So that's rate per period. Now we need to find still J2, right? So J2 will be this I2 times 2, right? So times 2. Now in my calculator I kept actually unrounded value of this. So that's going to be a precise answer right now. So J2 is going to be 3.96%. 3.96%. Remove this clutter. 3.96% compounded semi-annually. And that's now my nominal rate. Okay? So 3.96% compounded semi-annually is the same as effective rate of 4%. Okay? Again, because compounded semi-annually is more powerful than compounded one time per year, which is compounded annually rate. Therefore, it's a little bit lower to compensate for that. Okay, just for you to get used to this effective rate idea, let's just throw back a little bit to earlier topic of discussing finding rate, but I'll phrase that now in terms of effective rate, okay? So for example, you can meet effective rate in a problem like this. Okay, maybe Janet took a loan of $4,000. Okay, she paid $570 interest after 2 years and 5 months. So what effective rate was charged on the loan? Well, this is just a regular find a rate problem, but disguised with these words effective rate, right? But we already know that effective rate is rate compounded annually. So if you want to find this effective rate, okay, we first need to know what compounded annually rate will give you $570 or give Janet $570 of interest, right? So that's actually the problem for I, right? So let's use that formula for I in this case. So what is our future value? Future value is 4,570, and then we divide by present value, which is 4,000. 1 over n. Okay, so 1 over, how many periods are there? Well, in effective rate, that's the rate compounded annually. Therefore, it's the number of years that is going to be your period. So 1 over 2 plus 5 over 12. That's how many years that will be, right? 1 over, here it's 2 plus 5 over 12, because 2 years and 5 months is 2 whole years, and also there will be fraction of the year, and minus 1, of course. So let's see what this I is equal to. Okay, so it looks like it is 5.67%. Now, I here is the same as J, which is nominal rate, which is the same as F, your effective rate, right? It's all the same thing. So the answer is going to be 5.67% is the effective rate compounded annually, which is helpful to verify if we found it correctly, and for you also to see how effective rate is actually in terms of application. So we can always find future value, invest $4,000, it's $4,000, 1 plus 0.0567. So we invest at this rate, which is compounded annually rate, for exponent will be 2 plus 5 over 12. Okay, so let's calculate that. So 4,570.29. 70.29. You can see that, of course, this corresponds to this interest, but we have that extra part here due to some rounding of the effective rate. Okay, so that's basically a problem to highlight how you would use effective rate in your problems, how that effective rate concept can arise in your problems. Always remember, just replace that effective rate by the rate compounded annually. I actually want now to show you one more problem, which will highlight why simple rate does not stay equivalent for terms longer than 1 year if you found equivalency for 1 year, okay? Which is true for compound rates. So compound rates, when they're equivalent for 1 year, they are always equivalent. But for simple rate, it's not the same. Okay, so let's have this situation now. So Morrison took a loan of, say, $10,000 at 3% PA for 6 years. So what nominal rate compounded monthly would give him the same benefit. So Morrison took a loan of $10,000 at 3% PA for 6 years. What nominal rate compounded monthly would give him the same benefit? Okay, so we need to pay attention to this fact that it's PA, right? Simple rate. Remember, if no compounding is mentioned here, it's a simple rate. So now let me try to build equation for whole 6 years. Okay, let's say that I invest $1 for the whole duration of 6 years at 3% PA. Now, why do I invest $1 but not $10,000? Will be clear from this equation. Okay, let's say I invest 10,000. So I'll show now why $1 investment is enough, and actually this information would be even superfluous in this problem. Right? If I invest $10,000 at this simple rate, so it will be 0.03 times 6 for all 6 years, that will be equal, that should be equal to $10,000 invested at some rate I for the same 6 years, right? So, and this rate should be compounded monthly times 6. Okay. So this is the equation which basically will help you to find this I. And this equation ensures that this I, which is a periodic rate compounded monthly, will be equivalent to 3% PA annual simple rate over the course of 6 years. But first thing you will notice is that from both sides of this equation, we can delete $10,000, right? So we divide both sides of this equation by $10,000, which proves the point I was making, that it's enough to invest only $1, not worrying about investing this all $10,000. So $10,000 can be gone, and in this problem, I could find this equivalent rate without even using this $10,000 in the first place, by investing only $1. Okay, so now what is left here is this equation. Here is the thing. You see, 6 years is absolutely crucial here. There is no way for me to delete this 6 years from both sides of this equation, because that's simple interest here, right? And here it's not an exponent, it's a multiplication by 6, but here it's an exponent. You need to realize one thing, and that's very important, is that if this 3% was a compounded annually rate, right? If it was just compounded rate, the 6 would be an exponent here, right? So let's just imaginary, like right here imaginarily, right? So 6, it would not be here, right? It would be here if it was compounded annually rate. But in this case, you could delete this 6 from both sides and just deal with 1 year only. And if those compound rates were equivalent for 1 year, they would be equivalent for all the time. But of course, this is a simple rate in this problem, and therefore you have to put 6 here, which is not an exponent. So you cannot delete this 6 from both sides of the equation, which proves the point that for simple interest, when it is compared to compound interest, it is absolutely important to look at the whole term, right? So, for example, if now we find equivalency, and then 6 years becomes 4 years in another problem. So then those rates will not any longer be equivalent. Okay, so you will have to recompute that problem for 4 years. But let's now find this I from here. And the way you can do it is following the process that we outlined when we derived our formulas. Now we will have to find exponent, which is 1 over 12 times 6, right? So which is 72, 1 over 72 on both sides. It will be 1 plus 0.03 times 6, okay? 1 over 72. So you found exponent 1 over 72 here, and also 1 over 72 here, which gets rid of this part here. And 1 can be moved now to this side. So we have 3 times 6 plus 1 exponent 1 over 72 minus 1. So you have now 2.3. Okay, let me write it unrounded like this: 0.002230145 right? So J, which is compounded monthly nominal rate, is going to be this number times 12. And rounded to 2 decimals is going to be 2.76%. So 2.76% compounded monthly is equivalent to 3% PA over the course of 6 years, which is an important part. Okay. Just to prove a point, what if I put 1 year here, right? So what is it? What changes after 1 year? So of course $10,000 doesn't make any effect because it will be deleted from both sides, but this 6 will be gone here, this 6 will be gone here because it will be 1 year now in this another scenario, right? So this 6 will be gone. So let's see what happens after 1 year. Oh, one more thing here also, right? If I move from 6 years, so it's 1 over 12 here. Okay? So that's important because the answer I was getting didn't make sense, and that is clear why. Because now, if it's 1 year only for compound, it becomes here 12, right? Not 12 times 6, and here it's going to be 1 over 12 that I need to take on both sides. Okay, so you will see that in this case, if you find J from this I, it will be different. It will be, I have to write it here, 2.96%, okay? Compounded monthly. And that's the point I was trying to make, okay? So this is not going to be any longer equal to this, right? Because it's 1 here, not 6 anymore. But for 6 years, that's the nominal rate, which is equivalent to 3% PA. But for 1 year, it's 2.96% compounded monthly. That is equivalent to 3% PA. As you can see, they are different, right? So they are different rates. 2.76 here, but 2.96 here. Because for when you compare one simple rate to compound rate, equivalency over 1 year does not imply equivalency over other number of years, in this case 6 years, right? But in compound rate, that actually is not the case. For compound rates, equivalency over 1 year is equivalency over any number of years. So if it was compounded annually here, you can change this 1 year to 6 years, 10 years, whatever. You will see that equivalent rates will be staying the same for compound rates. I leave it to you to practice with this, to explore it for yourself. Okay, but that's it for now. Bye for now.